Okay, welcome 30-1s to your lesson number 3 for exponents and logs. This whole first example talks about exponential growth and decay, and it uses an example about cultures or patterns, talks about time. We are going to skip over this because I actually don't even teach it when I'm in a regular class, let alone doing it online. So we're going to skip all of this stuff and we're going to jump right to what an exponential function is. So here it is on the next page. Just get my pen working. Okay, so an exponential function looks like this, and this is how it appears similar on your formula sheet. And what we're going to do is we're going to explore what are the characteristics of an exponential function. And so we're going to compare two different graphs. The first one, y is equal to 2 to the power of x, and y is equal to 1 over 2 to the power of x. So if you want to participate and you want to slow this down, if you wanted to go and fill in those table of values that are here in order to graph our two equations on our grid, you can pause me and go ahead and do it. Otherwise, I'm going to fill them in for you. And so what we're going to get for this first table, if I'm plugging it in here, remember, I'm going to get 2 to the power of negative 3, which is y equals 1 over 2 to the power of 3, which is y is equal to 1 over 8. So the first one is going to be 1/8. Then we're going to get 1/4, 1/2. We know anything to the power of 0 is 1. Then we're going to get 2, 4, 8, and 16. So I'm going to plot those points on my graph. So at 0, we have 1. At 1, we have a value of 2. At 2, we have a value of 4. 3, we have a value of 8. 1, 2, 3, 4, 5. And you can see that it's going to get exponentially greater. It's growing very fast. At -1, we were at 1/2. And it's really hard for me to get super close, but you're going to see a graph that looks like this. Now over here, it shouldn't actually touch your y-axis. It's just getting closer and closer and closer. Just really hard on my smartboard to kind of get that accurate. And you would see something like that. Now for the second one, let's do it in blue. When you have 1/2 to the power of x, when I put in that -3, well, that, when I distribute it, becomes this, which I reciprocate both of those to make them positive, and I actually get 2 to the power of 3, which becomes 8. So when you see that 1/2, it actually does the opposite. We're going to get 8, 4, 2, 1/2, 1/4, 1/8, and 1/16. And what we're going to see when we have this one is it still has that y-intercept because anything to the power 0 is 1, so 0 at 0, 1. But when we were at -3, we were all the way up here. And then when we were at -2, we were at +4. And you're going to see the opposite happen with that 1/2. And so what do you notice, if anything? Let's think about our transformations. What happened when we had something that looked like this? It was a reflection in the y-axis. And what does that mean? Well, if we have a reflection in the y-axis, remember, that's something like y equals 2 to the power of -x. My x becomes negative, which makes sense because if I reciprocate it and make it positive, we have this equation. And so that's the biggest idea that they wanted you to get out of this one when we have a base of 2 versus a base of 1/2. They wanted you to know these characteristics. Asymptotes, you guys remember what those are? A line that it's approaching but never touches. If we look at these two graphs, these actually never touch our x-axis. So we actually have an asymptote at y is equal to 0 for both of them. Now to fill in the rest of these characteristics, there is no restriction in terms of what I can plug into this x. So my domain is all real numbers, or negative infinity to infinity, and that goes for both of these. Now my range, well, if it can't equal 0 or be negative, because it doesn't matter what values I put in here, if they're negative, it just means that it's going down. We know that our y values are greater than 0. When we talk about an x-intercept, well, if y can't equal 0 or y is greater than 0, we know that there are no or none for our x-intercepts. And for our y-intercepts, we saw that they were both at 1. And those are kind of the basic characteristics that you need to know. When we had a graph for this one, which is the one we did in red, our graph was rising exponentially. Rising exponentially means that it is a growth. Negative, a graph that is going down, would be a decay. And those are the main characteristics that we wanted to explore when you have an equation in the form a b to the power of x. We just talked about what happens with that base. When our base was greater than, let's say 1, it was a growth, which we'll summarize later. And when your base was less than 1 but greater than negative 1, so a fraction, it was a decay. And just like anything, we need to know the original characteristics because you guessed it, we are going to transform them. Now this next one wants us to explore what happens when our bases are either greater or smaller. So we obviously know in our calculator, so everybody take out your calculators, we're going to plug in what happens when we have 3 to the power of x. Okay, so in my calculator, I'm just going to go ahead and put in y equals 3 to the power of x. So there it is. And then I'm going to put in my second one, which is 10 to the power of x. And we're just going to compare what happens to our graphs. Most of you probably can assume what's going to happen. It's probably going to grow a lot faster. So there's my first one, and there's my second one. So you can see that the red graph is quite a bit steeper. Now let's go ahead and plug in the other two graphs. So we have brackets 1/3 x, to the power of x. And then we have 1/10 to the power of x. And we're going to see what happens to those two. So we see a decay, there it is, and then we're going to see a steeper decay with the purple one. And so as you notice, the greater your base is, so the bigger the whole number, the steeper your graph is. So it's going to grow exponentially quicker. And so we can draw all of those on our graph if we want to. You guys can fill them in. But what we noticed was we had a graph, and all of them went like this. So this would have been 3 to the power of x. And then we would have had one that looked like this, which was 10 to the power of x. Then we would have had one that was a little wider, 1/3 to the power of x. And then our last one, which was purple, was a little bit steeper, and 1/10 to the power of x. And so that's what we should have noticed when we did our graphing or exploring of these graphs. So what can we talk about in terms of b? Well, we've already mentioned it. I already wrote it on the other page, that when we have b is greater than 1, your graph is going to rise as b increases. So b is 2 versus b is 10. Okay, that's what we mean by increasing. When we have a fraction and it's decreasing because 1/2 is smaller than 1/10, is bigger than 1/10. Right, so this is decreasing. It's going to fall more rapidly or more sharply than if we had 1/2. So if we have something without using a calculator, make a sketch of what these graphs look like. Well, my base is greater than 0, so it's going to be a growth. And there it is. 0.2, I mean, that's the same thing as 1 over 5 to the power of x, so we know it's going to be a decay. And that's all you need to know really about that base. The characteristics, once again, to just summarize, if we want to state the x-intercepts, well, we know there aren't any. There's none. State the y-intercept. For all of the graphs we've done so far, it's always been at 0, 1. Our domain for all of them was XER, and our range was greater than 0. I'll just put our interval notation just as a reminder what that looks like. And there it is. State the equation. Remember, whenever it says equation, we want it in the form equals, x equals or y equals, and it's y is equal to 0. And that's our characteristics of our base. Let's move on to the second parameter, which is a. What is a going to do? Now, if you remember our transformations, a was our vertical translation, and it stretched our graph vertically. So let's plug these into our calculators and see what happened. Okay, so I've gone ahead and I've plugged in my first three equations of my graph, and now I'm just going to hit graph. So there's the first one, there's the second one, and there's the third one. So what do you notice happens on this y-axis? You're going to notice that the parameter that we put in front, a, here it was 1, our y-intercept was 1. Here it was 2, our y-intercept was 2. And here it was 5, and our y-intercept became 5. And that is the significance of that a value. So a became our vertical stretch, which affected our y-intercept of 1. 1 times 2, it became 2. 1 times 5, it became 5. So if you know the original characteristics and apply your transformations, once again, we can figure out the new characteristics when we transform it and introduce a new parameter. Okay, so notice there's our graphs that we had. My shape's a little bit off compared to the calculator. We can fill in the chart. You can see that the value of a, we had 1, we had 2, we had 5, we have a half. Our value of b was always 3, and you can see that the y-intercept changed to what that a value was. So what does it do? It vertically stretches the graph and it changes your y-intercept. So without a calculator, without graphing, we could go ahead and see what's happening with our f of x. So this takes us all the way back to our first chapter when we want to write this in terms of f of x. Here, 3 to the power of x is f of x, so this is just y equals f of x. But here, there's my f of x, which is my 3 to the power of x, but I now have a 2 in front of it. Here, there's my f of x, but I have a 5 in front of it. And then here's my f of x, and I have a 0.5 in front of it. And that's just writing it in terms of f of x. So if a question ever asks you, write it in terms of a function f, that is all we do. Obviously, with our transformations, we have a vertical stretch about the x-axis by a factor. Remember, what we see is what we did. So our factor was 2, 5, and 0.5. 2, 5, 0.5. And those were the values that we had as a. Okay, so if we want to talk about what the effect of the parameter is, it's our vertical stretch by a factor of a. And that is it. Our y-intercept will now always be 0a unless we horizontally or vertically translate it, which we'll get into further. Okay, so we can go ahead and fill in all these characteristics. So I would suggest pausing me and filling them all in, but I will go ahead and fill them in as we go through it. Our y-intercept turned out to be a. We had no x-intercepts. The x-axis was our horizontal asymptote. Our domain was XER. Our range was greater than 0. When we talked about b is greater than 1, it was a growth. When b was between 0 and 1, I think I wrote that as -1 before, but it should be 0, represents a decay. When we have this, it will rise as B increases, and it will fall more sharply as B decreases. When we talk about those A values and we talk about stretching it, when A was greater than 1, this is called an expansion because it gets faster, gets steeper faster. When it's a fraction, it's going to be called a compression because it kind of looks like it's wider. And then when we say that A is less than 0, this is a reflection in our x-axis. Now that's A, so remember that would be me putting a negative in front of this, and it would look, instead of it going like this, it would now look like this. And that's it. So you have a couple examples here that we can quickly go through just to remember our transformations. So here, if this is my original function, and I now have a 2 in front of it, the 2 is a vertical stretch about the x-axis by a factor of 2. And this, remember, was a horizontal translation, 2 units right. Okay, for this next one, okay, there's lots of stuff going on. We have a vertical translation, 4 units down. We have a reflection in the x-axis. And we have a horizontal stretch because it's here by a factor. And remember, when it's on the x, it's lying to you. So instead of 1/5, it's a factor of 5. So again, that just goes all the way back to chapter 2 when we talked about our transformations. I've already kind of alluded to this one when we were doing our graphing. Okay, if I wanted to take this one and bring that 3 to the top, I would make it negative, which when I have this is my original and I went to this, it's a reflection in the y-axis. Okay, and that comes to our exponent laws. Okay, this last one, again, we can talk about the domain and range. This is something that if you were writing the diploma, you would 100% see as a question on the diploma, talking about the characteristics of a graph, and it wants you to do it, or the exponential function, and it wants you to do it without a graphing calculator. So when talking about the domain and range, I want to think about what's going to affect the domain. Right now, my domain is all real numbers. Is that going to change? Absolutely not. Me moving it 2 units to the left doesn't change it. So my domain is still all real numbers. But my range, originally, if it was just 4 to the power of x, it would have been y is greater than 0. But right here, I'm going down 6. So what's that going to do to my range? It's going to make my range greater than -6, and not equal to, just greater than. Now my y-intercept for the graph, remember, when you're not sure, go back to grade 10. Math 10C, we learned that to find a y-intercept, we make x is equal to 0. So I'm going to plug in my 0. I get 4 to the power of 0 plus 2 minus 6, which is 4 squared minus 6, which is 16 minus 6, which equals 10. So my y-intercept is 0, 10. Now, a horizontal asymptote, an equation. Well, remember, originally it was here, but I moved it down 6. So now it's here. And so I'm going to get y is equal to -6. An extension to this last question is we could ask for a y-intercept, or sorry, an x-intercept. Remember, that's when we make this equal to 0, but we are going to need our next topic, which is called logs, in order to find that exponent. And that is what we will do starting next class, or next week. So that's it for lesson 3. Yeah.